Hi everyone, this is Sachin Kumar pursuing PhD degree from Material Science and Engineering Department, IIT Kanpur. Till now, in this diffusion in solid video series, solid video series, we have come across the what is diffusion, Fick's law, continuity equation, and solution for the different diffusion equation. Diffusion equation, concentration profiles, so if I missed any of these, any other topics that I teached covered in this one or yet to be covered, so please write it in the comment box section. Now, in this video lecture, we are learning about vacancy formation, resistivity measurement, experimental determination of enthalpy of formation, enthalpy of vacancy formation, so experimental determination of enthalpy of vacancy formation, P of vacancy formation, right? Okay, these are the topics covered and these are yet to be covered. Covering, yet to cover. So today we will learn about the vacancies. So what is vacancy? So vacant atomic site in a crystal is a regular is a missing of an atom from a regular crystal structure is called vacancy. Vacant atomic site in a crystal or a regular atomic site with an atom missing from its site. Regular atomic site with the atom missing from it. Missing from it is called vacancy. So without vacancy, the atomic arrangement is like this. So this is without vacancy. With vacancy, according to the definition, there is a missing of an atom from its regular site. So here it is missing, and this is called vacancy. And there are n identical atoms on n atomic sites. Here n identical atoms on n atomic site. That means the probability will become 1 for the with zero vacancy. If we create a vacancy, then there is an n possibilities of ways that vacancy will be filled. Then the configurations will increases, and in terms of the configuration and entropy will also increases. The vacancy is a stable point, and they are called as a stable point defects. I will write it in the form of the sentences. First of all, if we create a vacancy, then there is a n possible ways that the atom can be, then the vacant sites site will be filled, right? This will leads to increase in the configurational entropy. Okay, this entropy configuration entropy will increases. That is given as delta S1b. So we now know the how the entropy will changes. Okay. Next, we are knowing about the enthalpy. So by creating a vacancy, I will write a configuration. Here the vacancy is created. To create this vacancy, these are the atomic bonds between the atoms. Okay. So to create this vacancy, we need to break this bonds, right? So to break these bonds, we need some external energy or enthalpy to create this vacancy. Then we can write to create vacancy, the atomic bond should be broken. Should be broken, right? So then the enthalpy will increases. So now we can write it as the overall. We know that the entropy will also increases. First term, configurational entropy delta S increases. Second, delta H will also increases by forming the vacancy. Then the delta G for creating one vacancy can be calculated as delta H 1V minus T into delta S 1V. Okay, this we can write it as the box so that it's very important. It's a free energy required to forming the one vacancy. I will write this one also. Delta G1V gives free energy for the mono vacancy, gives free energy G of mono vacancy, and delta S1V is by configuration entropy. This one I think I explained in the previous sessions. Configuration entropy and the vibrational entropy. And this is due to vacancies, and this is due to thermal energy. Okay, so this is for the one vacancy. When we are forming n number of vacancy, vacancy, then one V is equals to n into delta H 1V minus T into delta N vibration minus T into delta S configuration 1V configuration. Okay, this is a overall equation. Considering the entropy both the directions. So how this thermodynamically forming the mono vacancies, how these vacancies are formed? So creating an atom, creating an vacancy within the system is a reversible process. So we are considering a one crystal completely, and we are removing the one atom from here, and we are adding. So we are adding the atom at the top, so that the number of the half of the bonds protons are conserved. So to create the complete vacancy, there is a half of the enthalpy is consumed. Then we can write it as delta H 1V is equals to half of the sublimation. Okay, so this is very important. I will explain how it is. What do you mean by enthalpy of sublimation? This means, so we are removing the one atom from the innermost, and it is completely removed from this whole system, and it is not at all coming back to the systems. And hence, to break these bonds, for example, here we need four atoms. Four bonds should be broken. Okay, so it's only number. Consider only the number, not a conceptual number. So, for example, I will write with the value itself so that it will be very easy. Okay. So to break these bonds, to break these four bonds, we need 8 as an enthalpy. 8 enthalpy, 8 kilojoules per mole enthalpy is required for the complete removal of an atom from the system. But we are not completely removing, we are creating this uh, vacancy, and we are keeping this atom on the top of this one, on the another side of the another side of the crystal structure, so that the mass balance, conservation of the mass is maintained. Then half of the bonds are retained. Then the and we are removing only, we are taking the 4 kilojoules per mole of enthalpy for creating the one vacancy, and this is by mass balance, conservation of mass. Okay, this is a overall concept of enthalpy. I will tell some of the example. Delta H sublimation, half of the delta H sublimation is there, and the experimental value for determining the forming the one vacancy. This is a proof. For platinum we are having 5.6 electron volt, and half of this one is 2.8 electron volt, and the experimental value to forming the one single vacancy is almost equal to 1.5 electron volt. For whereas copper, it's 3.3 electron volt. Half of 3.3 is 1.66 electron volt, and the formation experimentally determined is 1.28 electron. The effective, the experimental value is close to the, it's not at all close to the, it's little bit difference is there, and this is due to, I will tell the reason behind this one. The reason is the electron charge density will changes because of a removal of the atom. There is an electronic rearrangement is maintained to maintain the charge neutrality. Because of this one, the enthalpy of mono vacancy formation is less than that of the half of the sublimation enthalpy of sublimation. The electron density will changes because of a removal of atom. And there is a electronic rearrangements manual to maintain charge neutrality. Because of this, enthalpy of monovacancy formation is less than half of the half of the enthalpy of sublimation. Okay, this is all about the enthalpy of sublimation. Now we will consider the models to forming the enthalpy of formation of a monovacancy. The swelling is model for the formation of delta H1B in a copper. For delta H1B in a copper. First, we will remove the atom from the interior. First step, sublimation of the Cu plus from the interior ion, creating a sublimation of Cu plus from interior. So we can write it as Cu plus solid from the interior to Cu plus gases up to infinity. Second is sublimation of the electron from a interior. Sublimation electron from interior, that is given as electron sublimation from an interior to electron in the gaseous state infinity. Third step is, after this electron is also removed, Cu plus is also removed, then these two will combine to forms an atom. Combining electron with the Cu plus ion. That means we can write it as Cu plus gas at infinity plus electron gas plus infinity is given as Cu gas infinity. So putting this Cu atom back on the surfaces. Putting Cu atom back onto the on the surfaces. Then Cu gas infinity can be written as Cu solid on the surfaces. Then after this, there may be a one more electronic relaxation will also take place due to this settlement of an atom. And sixth one is elastic relaxation will take place. Will also take place. So this is a small model that has been given by the swelling, and it's a very simple model to create a one vacancy and calculating the delta H1 value. Okay, so by this he has created and given the value as delta H1V for Cu is almost nearly equal to 1.33 electron volt, but experimental value is nearly equal to 1.28 electron volt. Okay, now we are moving towards the expression for the formation of concentration of formation of mono vacancy. So I will derive the expression. Expression for X1, that is the concentration of one vacancy. So first of all, I will define the term X1V E is nothing but equilibrium vacancy concentration. Equilibrium vacancy concentration. And there are totally n number of atoms are present in a forming a n number of vacancies on n plus n sites. Then we can given the Gibbs free energy for the formation of one vacancy is equals to n into delta H1V minus T into L delta S1V vibration minus T into delta S1V configuration. So this is a basic equation that I have written previously. Equation 1. Then I have written this probability of configuration that n plus n c n. There is a combinations of formation of n vacancy with the n plus n sites can be given by the combinations formula, that is n plus n factorial divided by n factorial into n factorial. So then the configurational entropy forming one vacancy is given as k into ln omega. That can be k into ln n factorial into n. From the Stirling's approximation, ln of x factorial is given as x into ln of x minus x value. Then this can be written as delta S configuration of 1V equal to k outside into n plus n ln of n plus n minus n plus n minus n into ln of n, this plus n minus n into ln of n plus n, and this one more last one is this, it cancels, and this will result in the formation of minus k into n into ln of n divided by n plus n plus capital N into n into n plus n. So the vacancy concentration is very small. As compared to that of the total number of the sites. That's why this is almost equals to 0 and it is neglected. Then finally we will get it as this equation. Sorry for the interruption. This is not equal to 0. This is not equal to 0, as we know that n is too small as compared to that of the n. Then here is neglected, n plus n is nearly equal to capital N. Then this will become a 0 equal to 1. Then this will become 0. And here it is n into ln of n divided by capital N. Then this will x1 be the concentration. Delta S configuration of 1B is given by minus k into n into ln of x1b. Then delta G 1b dash is given by n into delta H1b minus T into delta S vibration into 1b minus plus k into T n into ln of x1b. So we can differentiate this equation with respect to vacancies. Then we given as like this delta H1b minus T into delta, here it is n is written 1b into vibration plus k into T ln of x1b. Okay, this will equal to the equilibrium number of the concentration can be calculated. Then the x1b equilibrium can be given as exponential of, by rearranging these terms we can get it as exponential of delta S1b vibration into k exponential of minus delta H1b divided by k into T. This is the final expression that we got. So expression that we got from the complete derivation. But delta S1b vibration can be ignored because of experimental errors are greater than that of the delta S1b. So this can be written from 1 to 2k value. Then finally experimentally we delta x1b e is given as exponential of minus delta h1b divided by kt is there. So from this equation, so we can have some conclusions. Take home messages. The vacancy concentration will increases exponentially with the temperature. So at near melting temperature, that is Tm, x1b, equilibrium is given as 10 to the power of minus 14. 4. That means in every 10,000 atoms, we can find the one vacancies. This is a maximum value. So one more term will comes into in this is a takeaway message. So one more vacancy term, that is die vacancy. So we already talked about the single vacancy formation. So usually we will find the number of vacancies at a single position site. Then they are called as a die vacancy, tri vacancy, or then in general we can write it as poly vacancy. So die vacancy, tri vacancy, and poly vacancy. If more than one vacancy is present at a time at a time at a single position, then it is called vacancy cluster. Okay, so this is a vacancy cluster. Example for this vacancy cluster is written die vacancy, so tri vacancy, etc. If a pair of vacancies is present, they are called as a die vacancy. Okay, so this is all about the basics and the derivation of a vacancy formation. In next video lecture, we are deriving the equilibrium on concentrations for the die vacancy and experimental determination of the vacancy formation. These two concepts will completes the vacancy formation in the material. Okay, so this is all about the vacancies. Thank you.